All right, in this video, I'll be going over the derivative of the natural log function and then a different technique that we call logarithmic differentiation. So I think the differentiation of the natural log function will be kind of nice because it's at least conceptually sort of similar to the inverse trig functions. The derivative doesn't look the same. They're in no way the same function, but the reasoning behind it or how you establish it is somewhat familiar. And then the concept where, you plug in the inside into the denominator is somewhat similar. So I'll show you what I'm talking about by actually running through it. All right, so let's start by just getting the general form of the derivative for the natural log. So much like that sine inverse function that we talked about when we began the last set of notes, if I asked you, hey, take the derivative of this function, f of x is ln x, you'd look at me and say, I don't know what the derivative of the natural log of x is. And I'd say, okay, well, what makes that hard? And you'd say, well, the natural log in front of the x. I don't know how to work with that. So the idea is the same as what we did with the sine inverse, and that is if we can somehow undo this natural log, then we don't have it there. We can maintain something that we can work with a little bit more easily. So in order to undo the natural log, we have to remember what the inverse of the natural log function is. So little review here. I am going to erase this, but I'll write it just so you can see it. This, I want to say I teach this in Math 99. I don't know if they cover it in 98. I don't generally teach Math 98, but in Math 99, we talk about log base e. Okay, well, log base e of x is really the same thing as the natural log of x. So the idea with logarithmic properties is if you have e to the log base e, these two undo each other and you're left with the x. In the same fashion, if we take e of the natural log of x, since natural log is really equivalent to log base e, it's just equal to x. So what we're going to do is exponentiate both sides of this equation. All right, so what that's going to look like is I'm going to take this equation and I'll have e to the f of x on one side and e to the natural log of x on the other. Right, from what I just discussed, we know the e will undo the natural log. So we have e to the f of x equals x. Okay, this is super awesome because when we take the derivative, we know how to take the derivative when we have e raised to something, and we know how to take the derivative of x. So let's take the derivative of both sides. All right, looking on the left-hand side of this, we should recall from the chain rule that we can have e as our outside function here, and f of x as our inside function. Right, so if we take the derivative of our outside function, we have e, and it doesn't really matter what color I guess, but I'll stick with blue since I called that function blue. Okay, so we have e to whatever's on the inside, which we decided was f of x, or I guess I decided, but I'll say we. Okay, so we have the f of x in there. I need to multiply by the derivative of the inside. So I have times f prime of x. And then moving over to the right, the derivative of x is just 1. Okay, so here, when I look at this, I think, okay, this is good. This is great because I know that I have the f prime in there and I'm trying to find the derivative of f since I originally called this function f. All right, so I'm going to divide the e to the f of x over. So I have f prime of x is equal to 1 over e to the f of x. Right, now I need to recall that really f of x was equal to the natural log of x. So since I knew f of x was equivalent to the natural log of x, I can go ahead and substitute that in. All right, and a quick side note, I forgot that I did not have my headphones in, so I'm sorry if there's a little bit of fan noise. Hopefully it's better now. Okay, so let's substitute that in. I have f prime of x is equivalent to 1 over e to the ln of x. All right, this is way nicer than the sine inverse because we don't have to go through all that substitution and crazy stuff we did last time. We can just say, oh, sweet, the e undoes the natural log, so really f prime of x is equivalent to 1 over x. So these two undo each other, the x is left over. Awesome, we're done. So the big conclusion here is that the derivative d dx of the natural log of x is equivalent to 1 over x. So what this means is anytime you're taking the derivative involving the natural log, the derivative is going to take this form, but if you have something else on the inside of that natural log function, that's what you'll be putting in the denominator. Key thing to note here, I'll probably erase this, but I'm going to write it in. All right, this is not multiplication. So a lot of times in when I teach in class, when I say this, people laugh at me, but a lot of times people be like, all right, so I have the derivative of the first, so ln prime times the second plus the first. Okay, it's not ln times x, it's ln of x. So please remember that is not multiplication. It's a pretty big error to think of that as times, because then you're saying you can take the natural log of nothing, which just doesn't make a lot of sense. All right, so now that I've went through that, let's just go ahead and use this several times. Should hopefully be kind of nice to work with. Alrighty, so first example, let's suppose we have f of t is equivalent to the natural log of, not times, of 4t plus t cubed, right? So looking at this, we hopefully can see that we have a big outside function, and that's that natural log function, and we have a little inside function, and that is the 4t plus t to the third function. So I'm going to go ahead and take the derivative here. When I do so, I would write f prime of t is equivalent to, all right, now I need the derivative of the outside. So I see this natural log and I think, okay, I need to write 1 over, and then the denominator here is just what's on the inside. So that would be 4t plus t to the third. I still need to multiply by the derivative of the inside. So when I take the derivative of the inside, the derivative of 4t is 4, plus the derivative of t cubed is 3t squared. All right, so that would mean my final answer, and you really could leave it like this if you wanted to, but I'll write this as 4 plus 3t squared over 4t plus t cubed. So technically this is like writing this over 1, multiply across, and that's what you get. All right, let's move along to the next example, and in this one, this is supposed to be an a there. Okay, I'm going to consider the function a of t is equivalent to sine of t squared times ln of 3t plus 4. All right, so I'm going to do this in Leibniz notation just because it started in Leibniz notation, but prime notation is fine too. Since I have the multiplication here, I'm going to spell out the product rule first. Therefore, I get dA dt is equivalent to, I need the derivative of the first, so I'll write this all out. That's sine of t squared prime, all prime, times the natural log, so times the second, which is the natural log of 3t plus 4, plus the first function is sine of t squared times the natural log of the second, so that's ln of 3t plus 4 prime. All right, so going through this, our first derivative is at least one that we've worked with before, okay, meaning nothing new here. Just going to apply the chain rule. So on this, I notice that my big outside function is sine. My little inside function is t squared. So the derivative of the outside would be the derivative of sine, and that's cosine. I need to fill the inside back in, so I'm going to put the t squared back in there. And then multiply by the derivative of the inside, so the derivative of t squared is just a 2t, so that's times 2t. All right, I'll rewrite the natural log, so times the natural log of 3t plus 4. Rewrite the plus, rewrite the sine of the sine of t squared. That doesn't look very nice. Come on, there we go. Okay. All right, now I need to take care of this natural log to the natural log of the 3t plus 4. So again, I use that of verbiage. I know I'm going to apply the chain rule. My outside function here is that natural log function. The inside function is going to be this 3t plus 4. All right, so going through this, I know my outside function is the natural log function. So I'm automatically going to say, okay, so I have times 1 over, do that when I see the natural log. Now I know the bottom here is really just what's inside of the function. And that's 3t plus 4. And then I'll multiply that by the derivative of the inside. So the derivative of 3t is 3, the derivative of 4 is 0. Therefore, I've taken this derivative. If I want to, I can go through and multiply these together and rewrite the whole thing, but it's also fine to leave like this. So that would be my final answer. All right, so hopefully that gets you the concept of what to do with those natural log functions. Of course, you'll have many things intermixed: product rules, chain rules, quotient rules, etc. They'll get tougher, maybe some of them will be more easy, but the main idea is as soon as you see that natural log of, you know you're gonna have to use the chain rule somewhere, and then you're gonna write 1 over whatever is on the inside of that and not forget to take the derivative of the inside. All right, so I wanna move on to logarithmic differentiation. Logarithmic differentiation is more of a technique rather than just the derivative of this is this. So I know when I just did the natural log, I'm like, all right, generally the derivative of the natural log looks like this. The logarithmic differentiation is more so a technique that we use. We use this technique when we have a function or a variable raised to another function or variable. So thinking back to what we've done, if I have a constant raised to a value, or if I have a constant raised to a variable, or if I have a variable raised to a constant, I know I can use exponential differentiation or the power rule in the second case. Okay, this is a little bit different. So what you first have to do is recognize if you have a variable to a variable, or a variable to a function, or vice versa, a function to a variable, a function to another function, that clues you in that you're going to use this technique. In this technique, which I'll go through a couple of times, the first thing that you're going to do is take the derivative of both sides. Sorry, take the natural log of both sides. What that does is allows the exponent to drop down, so then you don't have to worry about it being stuck up there anymore. After you do that, you'll differentiate both sides, and then you're going to have to do a little bit of algebra to solve for the derivative. Key thing here, algebra will come into play when you do some of these. Properties of exponents is also going to come into play, and properties of logs will come into play. So it will require a little bit of prereqs. I encourage you to look up properties of logs if you know you're a little bit rusty or a little fuzzy on those. All right, let's start with a relatively basic example first. So I'm going to focus on the function f of x is equal to x to the x power. I want to find the derivative df dx. Real quick, I just thought of something. Sorry, up here I ended up using the prime notation. That's fine, I'm not going to go through and change all of it, although usually I'd go through with a Leibniz notation, but it's okay right now. Anyway, on this, I'll try to remember to use the Leibniz notation the whole time. Okay, so when I look at this function, I think, okay, I have a variable raised to a variable. The reason this is difficult is because you have this variable stuck up here in the exponent and you don't have a technique for that yet. However, we now have been introduced to this concept of a technique, and that's of logarithmic differentiation. So I'm going to do my first step, and I'm going to take the natural log of both sides of this equation. When I do so, I get ln of f of x, okay, equals ln of x to the x power. Right, by properties of exponents, I'll write this out, by logarithmic properties, by log properties. Okay, remember natural log is really log base e, so it's okay to say log properties there. I have ln of f of x is equivalent to the x drops down in front to get x ln x by those logarithmic properties. Now I'm going to go ahead and take the derivative of both sides. So that would be d dx of the left, okay, and d dx, I'll squeeze that in there, of the right. Right, I'll try to spell this out so we can hopefully see everything. On the left-hand side, I have the natural log of another function, which means I'm going to use the chain rule. So my outside function is the natural log. My inside function is f of x. Right, taking the derivative of the outside, since I see that natural log, I know I need to write 1 over. I'm going to fill my inside back in, so that would be f of x. And then I'm going to multiply by the derivative of the inside. So if I use the Leibniz notation, that would be df dx. If you use prime notation, it'd be f prime of x. Right, this is equivalent to, okay, the derivative of x times ln x. So I know I need to use the product rule there. So that'd be the derivative of the first, so x prime, times the second, natural log of x, plus the first, so x, times the derivative of the second, so natural log of x prime. I just realized I didn't use a Leibniz notation again, so I'm going to erase these and write that back in. So rather than prime, I will write a ddx of x, and I will write a ddx, that's messy, a ddx of the natural log of x. Okay, so x ddx of ln x, there we go. Okay, so I'm going to leave this left-hand side alone and just rewrite that for a moment here. All right, let's go through and take those derivatives on the right. So the derivative of x with respect to x is just 1. So I'd have 1 times ln x, which is just ln x, plus, rewrite the x. The derivative of the natural log of x that we discussed earlier is 1 over x. All right, so now I'm going to do two things at once here. First, I'm going to go ahead and multiply this f of x over, and that's because I'm trying to find df of x, so I want to isolate it. Therefore, I get df dx is equivalent to f of x times ln x, and this is a pretty gentle simplification, so let's simplify that. X times 1 over x is just 1, so I get a plus 1 there. All right, now I'm going to go ahead and remember that f of x was equivalent to x to the x from the beginning of the question. So by substitution, I have df dx is equivalent to x to the x times the natural log of x plus 1, and that would be my final answer. So key thing here, when you take the natural log of both sides like that, it allows you to drop that exponent down, so then you have something a little bit more familiar to work with and really something that you can work with. So you can't use the exponential rule, you can't use the power rule when you have a variable to a variable. All right, let's try another one. This one a little bit more complex, but similar in reasoning and technique. So let's consider h of x is equivalent to sine of x raised to the natural log of x. So here, sine of x is in fact a function. The natural log of x is also a function. I have a function raised to a function, which clues me in, okay, I need to use that logarithmic differentiation. I'm going to begin by taking the natural log of both sides. So ln of f of x is equivalent to ln of sine x to the ln x. All right, here, by properties of exponents, I can drop this ln x out in front. So I have ln of f of x, keep the left the same, is equivalent to ln x times ln of sine of x. Right? Going from here, when I look on the left, it's going to look exactly the same as what I just did in the first example for this type of differentiation. So with the chain rule, the outside is the natural log, the derivative of the outside is 1 over, keep the f of x down here, times the derivative of the inside. All right, calculate f prime of x. I'm just going to stick with the prime notation here. Or sorry, h prime of x is what I'm looking at. There we go. Okay. So I guess I should put h's in here, although the concept's the same. So let's put an h and an h to be consistent. There we go. All right, there we go. So I have 1 over h of x for the outside of this times the derivative of the inside would be times h prime of x. Moving over, excuse me, to the right-hand side. Okay, if I read this aloud, I have the natural log of x times ln of sine of x. Therefore, I need the product rule. Ln x is my first function. Ln of the sine of x is my second function. Right, I'll write all the steps out here, just spell out that product rule. So the derivative of the first is ln x prime, times the second is times ln of sine of x, plus the first is ln x, times the derivative of the second is ln x sine x prime. All right, so I'm going to leave the left-hand side alone here and just rewrite it. Go. Okay. Working with the right-hand side of this, the derivative of the natural log of x is 1 over x. Then I'm going to rewrite the times ln of sine x, plus I'll rewrite the ln x. Now I need the derivative of the natural log of the sine of x. I need to recognize that this requires a chain rule. My outside function is the natural log function. My inside function is sine of x. So the derivative of the outside, since I have a natural log, is 1 over, fill the inside back in, so I get sine x, and the derivative of the sine of x is the cosine of x. All right, so I've taken the derivatives completely. Now I just have some algebraic cleaning up to do. To isolate h prime of x, I'm going to multiply h of x over. So I have h prime of x is equivalent to h of x times parentheses 1, actually, I won't even write 1 over. Okay, so here I can just multiply the 1 by the ln sine x that's in the numerator there. So I get ln sine of x over x. Takes care of this chunk right here, this first chunk, plus, right? I'm just going to write this a little bit nicer. So up here I have ln x times cosine x. Put a little parenthesis around there so you know that cosine is not inside of that natural log, all over the sine of x. And for a final step, I'll do my substitution. So by substitution with h of x being equal to sine x to the ln x. I think that's what we started with. I better double check here. Yep, good. Okay. I know that I get h prime of x is equivalent to sine of x to the ln x times ln sine of sine x over x plus ln x times cosine x all over the sine of x. All right, I've fully and completely taken the derivative. I've done my back substitution. I'm done here. So with these, this one's probably medium to maybe hard difficulty. Sometimes you'll have to recognize properties of exponents, properties of logs, but the general concept is going to be the same. So this should give you enough of a tool to go off as long as your prereqs are okay. Review your prereqs if you need to, and then ask questions. And if you miss some prereqs, I can try to help you catch back up on those or notice where they apply at.